Okay, welcome back. Just to quickly remind you where we are, we're still looking at the linear least squares. So we're trying to model some measurements using models which are linear in terms of parameters. So the model is a linear combination of some basis functions. So then we turn the minimization problem into a linear algebra problem to minimizing a quadratic form. We differentiate it, we do a little bit of math, and we arrive at the system of normal equations, which is a system of linear equations for unknown parameters beta, that's a vector of unknown parameters, and the left-hand side is given by the product of the transpose of the design matrix with itself. And like I was saying previously, the condition number of this normal system can be reasonably bad because it's just a square of the condition number of the design matrix itself. So this solution of this normal system can be a bit problematic. Solving this normal system can be a bit problematic from the numerical standpoint. Let's see what we can do instead of forming this normal system explicitly. One way is based on the QR factorization, which we discussed a while back. So just to remind you, any matrix, including, say, a rectangular one, can be factorized into a product of an orthogonal matrix, let's call it Q, and an upper triangular matrix. So graphically, say if we have our design matrix which is thin and tall, we have this Q matrix, this is A, this is Q, and it gets multiplied by R, which is upper triangular. So necessarily it has this part which is non-zero, and the rest are all zeros. So let's call this non-zero part R1, which has dimensions of m by m. And this decomposition exists for virtually any matrix A, as long as it's not rank deficient. Okay, this is nice, but how do we use it? Here's how. What we're actually minimizing is a 2-norm of some vector in an n-dimensional space. A length of vector is invariant under rotations. So what we do, we rotate this vector of residuals by Q transpose. This doesn't change the length of this vector. And what we get once we open the brackets, we'll have our observation vector rotated by Q transpose. And in the second term, we factorize A into Q and R. Q transpose times Q is a unit matrix because it's orthogonal. So what we get is this upper triangular part acting on the vector of unknowns. Okay, then let's see. In the second term, we have the upper part of dimension m of something, and the rest is all zeros. So let's factorize the first term in the same way. We just name the first m entries by f and the rest by r. So with this renaming, with this splitting, the original cost function splits into 2 terms. One is independent of beta, that's just a constant term. And the second term we can do something, because it does depend on beta. And clearly the minimum of our cost function is achieved for the beta, which makes this first term equal 0. so that the minimum which we're looking at satisfies this linear system. And what is what here? So f is the upper part of the observation vector rotated by q, and q is the orthogonal part of our design matrix. So this f involves both observation points and independent variables. And r is this triangular, or r1 is the triangular part of the QR decomposition of A. And this r1 is actually triangular. So graphically, this system of equations looks like this. This is f, this is beta, and this is r1. So it can be just solved by back substitution very easily. So in a nutshell, the full algorithm for solving the linearly squared problems is like this. First, we factorize the design matrix into QR factorization. Then we rotate the observation vector by the orthogonal part. And notice that in the next step, we'll only need first m rows of the result, which was f. So we only need to perform a thin QR at the first step. And then once we've rotated the observation vector, we just solve for our target values of parameters by back substitution. And that's cheap. Okay, and this is all. This is exactly equivalent to solving the normal system of equations, but numerically this is often much better conditioned.